Good morning, Finite Math fans, and welcome to week 2 of Finite Math. Before we do anything else with sets, we're going to have to talk about Venn diagrams. And I've given a definition of Venn diagram. A Venn diagram of two sets, A and B, is a picture that indicates the exact location of all elements of the universe with respect to A and B. Well, that sounds like a pretty pompous boast, doesn't it? Here's how we draw a Venn diagram for two sets A and B. That we start out with our universe. And this big rectangle is our universe. So everything in the universe is inside this rectangle. Next, I'm going to draw sets A and B in such a way that every object in the universe can be accounted for by the way that we draw sets A and B with relation to one another. So here's set A. And here's set B. And I deliberately drew them so that they would overlap. That was very deliberate. The next thing that we're going to do with this picture is that we're going to divide everything in the universe into regions, such that if we put all of the regions together, we get the entire universe. But if we take any two regions, they don't overlap. So I'm going to call this region 1. I'm going to call this region 2. And I'm going to call this region 3. So an element that's in region 1 is in set A, but it's not also in set B. Any element in region 1, and this is region 1 right here. Any element in region 1 is in set A, but it's not part of set B. And region 3, any element that's in region 3 is in set B, but it's not in set A. It's not in this part that overlaps. Well, what about region 2? This is the set of all elements that are in both set A and set B. Now, as far as all of the possibilities are concerned, there's one possibility that I haven't taken into consideration yet. Do you know what that is? What possibility have I not considered with regard to set A and set B? Maybe an element is neither in A nor B. An element could be outside of both sets. And that is my region 4. So let's see, region 1. Region 1, over here, these elements are in set A, but they're not in set B. Region 2, Region 2, these elements are in set A and set B. And then region 3, these are the elements that are in set B, but they're not also in set A. And then finally, region 4. Now take a look at that for a few seconds. And then I'm going to do an example. Venn diagrams can be very helpful with counting problems. They can also be very helpful with logic problems as well. No, I don't think I want to do that. Let's see. B equals. Okay, I like that. So our universe is the set of all whole numbers from 1 to 11. And you know what? I'm just going to move this over here so I'll have more space on the board. I'm not changing the example. I'm just giving myself more room on the board. Okay, now I'm going to draw my Venn diagram. Here's my universe. Here's my set A. Here's my set B. And here's region 1, region 2, region 3, and region 4. Set A, all of the numbers from 1 to 6. How many of these numbers in set A are also in set B? Okay, I got to watch that, don't I? So 1, 3, and 5 are both in set A and set B. So they go in region 2. 1, 3, 5. 2, 4, and 6 are in set A, but they're not in set B. So what region do they go in? 2, 4, and 6 are in set A, but they're not in set B. So where do they go? Region 1. Okay. 2, 4, 6. Now, let's take a look at set B again. Elements 7, 9, and 11 are in set B, but these elements are not in set 1. So where do we put these elements in our Venn diagram? If they're in set B, but they're not in set A, where did they go? Maybe right here. So here's 7, 9, 11. They're in set B, but they're not in set A, so we put them in region 3. Now, does this account for all elements in the universe? Let's see. The numbers 1 to 6 are in set A. And the numbers 1, 3, and 5 are in set B. and the numbers 7, 9, and 11 are in set B. So what elements are not in set B and also not in set A? Let's see. 1 through 6, they're in set A. 7, 9, 11 are in set B. So it looks like 8 and 10 are neither in set A or set B. So we can put 8 and 10 out here somewhere in region 4. So this would be a Venn diagram that depicts the relationship of A and B as well as the universe in this example. And again, Venn diagrams can be very helpful in solving counting problems and in solving logic problems as well. And just because we're drawing pictures doesn't mean this is simple stuff. Originally, I'm an electrical engineer by training. And one thing I know about engineers is that they love to draw pictures, and they draw good pictures because a good picture or several good pictures are invaluable in problem solving. And when I was teaching electrical engineering, all of my best students were people who liked to draw pictures in their examples, and it served them very well. Now, I'm also a mathematician, and people who draw pictures to do applied problems in mathematics typically do very well also. So drawing pictures, well, this is kind of simple stuff here, but it gets more complicated. And just because we're drawing pictures doesn't mean we're doing second grade arithmetic. This is much more complicated than that. And something that every good engineer and every good mathematician knows is that good pictures lead to good solutions. Good pictures lead to correct solutions. This may seem like second grade math, but it's not. And all of my students who are humble enough to acknowledge that and draw good pictures turned out to do very well in academia and in engineering. So, let's continue on. One important feature of our discussion in sets is something called the complement of a set. The complement of a set A, and this is how we write A complement, is the set of all elements of the universe is the set of all elements in the universe that are not contained in set A. And for this, we're going to draw a Venn diagram just of set A. This is our universe. This is set A. And all of the elements that are not in set A are A complement. So let's do some shading here. So A complement is the shaded region in this example. Now let's do, I guess this wasn't an example. This was just an illustration, wasn't it? So let's do an example. Okay. An element illustrating the concept of the complement of A. Our universe consists of the whole numbers from 1 to 8, and set A is the whole numbers 3, 6, and 7. So where are we going to put 3, 6, and 7? Maybe right here in this A circle, right? If 3, 6, and 7 are in the A circle, then they're in set A. Now the rest of the elements of the universe, let's see, 3 is in A, 6 is in A, 7 is in A. The rest of these elements, 1, 2, 4, 5, 8, are not in set A. So they go outside of set A. We can put them anywhere outside of set A. 1, 2, 4, 5, 6, 1, 2, 4, 5, 8, right? Okay. Now, in this exercise, I didn't define A complement. I defined the universe, I defined A, but based on these two facts, I know what A complement is, don't I? A complement is all of the elements of the universe that are not contained in set A. So, A complement, that's the set that contains 1, 2, 4, 5, and 8. Okay, time for another concept. Okay, everybody, our next concept is the concept of intersection. And let's see, I guess we all drive a car. When we're driving, what is an intersection? It's a place where two streets meet, and right where they meet, if you're standing right where those two streets meet, you're actually standing in both streets, aren't you? Here's street A, here's street B, and if we're standing right at the intersection, right underneath the stoplight, if we're standing right there, we're actually standing both in street A and street B. That's the idea of an intersection when it comes to sets. The intersection of two sets A and B is the set of all elements in the universe that are contained in both A and B. So in our Venn diagram, A intersect B is region 2. Now, I guess I should make a remark about notation now. This is how we denote the intersection of A and B. This kind of looks like an upside down U. We look at this and we say the intersection of A and B, or sometimes we look at this and we say A intersect B. A intersect B is the set of all elements of the universe that are contained in both set A and set B. So we've defined the intersection. Let's look at an example. Back with another example. Here we have a Venn diagram showing us where the sets are, where the elements of the sets are, and so forth. And we're told, determine the elements of set A, set B, A intersect B, and the universal set. Okay. A. What elements are in set A? And set A is this entire circle, isn't it? So what would you say? 1, 2, and 3 and 4 are in set A also, aren't they? So 1, 2, 3, 4. Set B, what elements are in set B? 5 and 6 are in set B, aren't they? But elements 3 and 4, aren't they in set B? So 3, 4, 5, 6, they're in set B. Okay. A intersect B. Now, how did we define the intersection of A and B? Do you remember? A intersect B is the set of all elements that what? All elements that are in both set A and set B. So that would be region 2 here, wouldn't it? 3 and 4 are in set A, and 3 and 4 are in set B. So 3 and 4 are in the intersection of A and B. Now, could we have figured this out without looking at the diagram? If we had seen these two things, yes. That we'd look at set A and we'd look at set B and say, you know what? 4 is in both set A and set B, and 3 is in set A and set B. So they must be in the intersection of set A and set B. Okay, 3 down, 1 to go. The universe, the set of all elements. So every element that we see up here is in the universe, right? So 1, 2, 3, 4, 5, 6, 7, 8. All of them are in the universe. Voila. Well, maybe it's about time we do another concept. Back with another concept. The union of two sets. The union of sets A and B, and we denote it this way, A union B. Well, it looks like intersection almost, doesn't it? Except intersection had the upside down U. This actually looks like a U, and we might think U for union, okay? So A union B is the set of all elements of the universe that are contained either in A or in B, or both A and B. So, if an element is in region 1, it's contained in A, right? So region 1 is part of A union B. If an element is in region 3, it's contained in B. So it's contained in A or B. Anything in region 3 is contained in A union B. And what about region 2? Well, A union B is the set of all elements that are contained in set A, or in set B, or both. Well, this is both set A and B right here. So region 2 is also part of the union. So A union B is comprised of, or some people would say A union B comprises regions 1, 2, and 3. So this the shaded area is A union B. So if an element's in set A, it's in A union B. If an element's in set B, it's in A union B. If an element is both in A and in B, the element is in A union B. The only elements of the universe that are not contained in A union B are where? Region 4, right? The only elements of the universe that are not contained in A union B are the region 4 elements, those elements that are outside of both A and B. So let's do an example, simple example. One more example. Here's our picture. and the location of all elements is given. Determine the elements that are contained in set A, set B, A union B, and the universe. Let's just say A. One and two are contained in set A. What about 3 and 4? Yeah, 3 and 4 are contained in set A also. So 1, 2, 3, 4. Set B. 5 and 6 are contained in set B. Any other elements? 3, 4? Sure. 3, 4, 5, 6. And then it asks for A union B. There are a couple of ways that we can look at this. A union B is the set of all elements that are contained in A. Or B. Or both A and B. Now there was another way, well, there are a couple of ways that we could have done this. Maybe two other ways. Another way that we could have done this, just looking at the picture. What's another way that we could have done A union B just looking at the picture? We know that the only elements that are not in A union B are where? Region 4 here? Okay. So all of the elements that are not in region 4 are in A union B. 1, 2, 3, 4, 5, 6. So that was another way that we could have done A union B. Or, since we already knew what A and B were, we could have done A union B without looking at the picture. A union B is the set of all elements that are in A and all elements that are in B, or both. So we take all of the elements in A, 1, 2, 3, 4, all of the elements in B, 3, 4, 5, 6, all of the elements that are both in A and B, 3 and 4, put them all here. This is A union B. We could have done it that way too. Now, what about our universe? The universe is the set of all elements, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. That concludes the lecture for today. I'll save the homework until tomorrow, but watch the lecture today. Take some notes, and where you need to, hit the pause button. Be conscientious about this. This is summer, and this could be our best term in school yet. So enjoy it, but work hard. And if you work hard, you will enjoy it.